Okay, let's start our lecture. And today I want to introduce the most powerful tool of homological algebra, namely spectral sequences. We will consider its very particular case, but it already will be enough for very many applications for us. Okay, what the spectral sequence is? Okay. Spectral sequence of homological type, for example. So spectral sequence of homological type is the following thing. We have for P, Q integer numbers, and R, its natural numbers beginning from something. We have modules over some fixed ring, which numbered with these numbers, and this thing called R page. We have for any number R, we have page numbered by integer coordinates P, Q. In each coordinate we have submodule. It's R page. R is fixed. R is fixed, P and Q are integers. And we have differential. Differential has by degree, it acts on this page and has by degree minus R, R minus 1. So for any fixed R, for any PQ, we have differentials on this page. For example, if you have 0 page, on 0 page, it's by degree 0 minus 1. So on 0 page, it's such differentials. On the first page, it's by degree minus 1, 0. It's such differentials. On the second page, it's differentials of the horse move on chess. Yes, it's something like this. And so on. In general, if you have some elements, you consider the previous diagonal, and all differentials goes to the elements of the previous diagonal. It's differentials on different pages. But if you consider on different pages the element of the at the same point, then differentials act like in this picture. And what else? Okay, we have some pages. On each page we have differentials. What the connections between them? No, connection is very easy. Connection is that this thing is spectral sequence if homology of the thing. So we have some differentials here and here. Of course, we need to check that this thing is differential, so its square is 0. And so in each point, in each place, we obtain homology. And we need that this PQ plays homology of this thing under this differential. They must be isomorphic to the next place, the next page in this place. So we have first page, maybe we can begin not from 0, not from some number. We have the initial page and some differentials. We have homologies, it's the next page, but also we have differentials on this homology. We also have differential on the next page. And if we calculate the next homologies, we obtain the next one page, and we have differentials. Differentials is some data, it's some additional data. If you consider chain complex, you don't have, in general, differentials on this homology. Spectral sequence, it's when you have bigraded complex, bigraded differentials, and you have differentials on each next homologies. Okay? It's all. It's general spectral sequence. Now we will consider the simplest case, stabilized spectral sequence. Stabilization means that for any place there exists such big number, such that for each pages of the greater number, all differentials inward and outward from this place. This is and this is so P plus R Q minus R plus 1. They are 0 in this concrete place. For each concrete place, there exists such number that all differentials are 0 from some time, okay? From some page. Now, this means that at this concrete place, your calculation of homology is stabilized on some page. And then, no, all the homologies are the same because kernel is the same module and image is 0. So in each place, you have that then n isomorphic to n plus 1, isomorphic to and so on, okay? N depends on P and Q maybe. It's not important. Now then we call this infinity page at this place. And so for any place, you obtain infinity page. In fact, infinity page of this spectral sequence. There is no differentials in infinity page. It's just big-graded modules. Okay.
Can it be so since P and Q are from Z, this page is infinite. It can happen, I think, that this n, when we travel along, for example, this line, it can increase. I mean, for each square it's finite. But
in general, of course. In general, it may happen that such n doesn't exist. In general, this n can depends on P and Q. Of course, it can increase. Yes, it's already very strong property. In general, you have this property. In general, you have this property, and you have more subtle and more accurate definition of stabilization or infinity term. This is the simplest one. So because if you have the global n for any PQ, and it's a very rare situation, in fact. This n can depend on PQ. For example, the most usual example for us, for example, it's if you have that some page, maybe not initial, some page, is, for example, of the first quadrant and 0 in all other quadrants. Okay? Then in each place, you have some number that goes to 0 and goes from 0. And this number, of course, depends on the number of diagonal. It will increase. But it's okay. It's very good situation, in fact. Okay? For example, if you have some page of the first quadrant, then by definition, all next pages also is from this quadrant. And then you have this stabilization. Okay? Because very big differential goes to negative first coordinate and goes from negative second coordinate. Okay. Okay. Oh, it certainly depends on P and Q. Okay. Yes, and what spectral sequences do? They tries to approximate something. So no.
Why do we have such a weird rule for our differentials? I mean, EPQ goes to P minus R, P plus.
No, in fact, it's one of standard index conventions. You have some other conventions, but it's important that differentials have increasing B degree, because these differentials, they calculate approximation in some sense. It's important that they have increasing degree. In some conventions, they have B degree something like this or something like this, but it's important that they're different and they're increasing. Because you need to from its construction it works. Philosophically, it means that R's differential, it goes further than the previous one. It's by design. It's important. Concrete indexing conventions may be different. For example, this is also useful. For example, in atom spectral sequences, something like this. But it's important that B degrees are increasing. No, you will see from construction of the certain spectral sequence which works for our goals that it's true.
Oh, I understand that the mark there is always.
Maybe you will understand it from construction, from construction of spectral sequence of filter chain complex when it appears. Mhm. Yes, spectral sequence tries to approximate something. Tries to approximate something by its infinity page, and we say that spectral sequence converge stabilized here. Okay. I don't know how to write it. Okay, stub. To something, to what? It converges to some graded module and with filtration. We have that it's Hn. It's graded module, and it has graded filtration. So in fact, each graded component has an increasing filtration. So it has an increasing filtration. So if you have such filtered graded object module, then we say that spectral sequence converges to it. This means that infinity page, again in some indexing convention, but it's our indexing convention, PQ infinity page isomorphic to associated quotient in grading P plus Q.
Can you repeat this once again?
No, we say that spectral sequence converges to something, to what? What object can be the target? It's graded module with filtration in each grading. Mm-hmm. And we say that spectral sequence converges to this thing if infinity page is associated quotient in grading P plus Q, quotient in filtration P modulo P minus 1. It's increasing filtration. Of course, in general, you need something like in our situation, this filtration will be locally finite, which means that for each gradient, it's in fact finite. So in fact, Hn, it's F something, and then increase in filtration, and F K something is 0 in fact. So it's finite, and its union, its whole gradient component, and intersection is 0. It will be in our situation. And converging say that after infinite pages, after infinite steps, infinite page can reconstruct quotients. So we have two problems here. We have problem of calculating infinite many differentials and infinite many homologies. And in the final part, we have in fact a problem of extension. So because, okay, for example, we have finite extension, finite filtration maybe. Now then, what does it mean? This means that what is 0? The smallest part of filtration. This is 0. We have the following filtration. What's the quotient? Quotient must be this thing. It's infinity. Gradient is sum of P is quotient. It's K plus 1 and N minus K plus 1. Mm-hmm. But it's 0. So in fact, this filtration is exactly this infinite page. But we have the next quotient, next filtration. And this quotient is infinity K plus 2 N minus K minus 2. And so, in fact, we obtain, okay, we know the smallest part of filtration. But already for the next part of filtration, we have extension. We only know that we have a short exact sequence. Infinity k plus 1, n minus k minus 1. This filtration. And then quotient by them. So we know this part maybe after infinite many steps. But it's just extension. For example, for vector spaces, it's trivial. But for abelian groups, it's maybe not trivial. So we have infinite page extension problems. We have infinite many differential steps and infinite page extension problems. But anyway, it maybe we can say something from spectral sequences. And we will say something. Okay. But I just want to say that it's, of course, have some other difficulties. If you even have convergent spectral sequence, you have some difficulties in a way. Okay, it's understand? And then you have the similar extensions for any other filtrations. Okay. If you know then this one, then you have filtration. This one it goes to the next one, and then its quotient is k plus 3 n minus k minus 3. If you by induction know this and this, then you have extension for this, and so on. And at the final part, you have Hn itself, but you have some. You need to do some steps before this. Some extensions, some differential, infinite many differentials, and maybe finite number, but some of extensions for it in general. Okay.
I have a question. Two questions. First is why we have an injection from E infinity on the first exact sequence?
Because this quotient is E infinity, okay, by convergence, okay, and this is 0. So in fact, this quotient is this filtration, this injection. It's f k plus 1 hn, the first non-zero filtration, okay. It's important, yes, you're right, because we ended by zeros. The final quotient is just the final non-zero module, okay.
Okay, and the second question is, from this construction we can see that these calculations really depends on k. So I think
yes.
that these EPQ infinity are not, from this procedure, are not defined for arbitrary P and Q, but for...
No, here I assume that we know all infinity page, of course. Because you're right, I need to know for different numbers. I assume that we do all infinite steps and we know whole infinity page, okay? Then we can start to say something. No, of course, if you know not whole infinity page, we can say something about not each filtration, not each gradient. You're right. Yes,
so,
yes. It's some random numbers. In our session, we have some concrete numbers here of filtration and something. Okay. Mm-hmm.
So this was not the definition of E infinity P and Q. This was the.
It's definition of convergence. We say that spectral converge if this is true. It's converged to this thing.
Okay.
Infinity, I said before, its definition is that for each PQ, for some big numbers, all differentials are 0, and then all homologies stabilize. And this is infinity page. In each degree, we, after finite number steps, we can calculate it in principle, yes. And then, if we say that it's converged to something, it means that in fact we have some filtration on these modules, and we can hope that this isomorphism exists. No, in our situation, second before. Oh, sorry. After some seconds, I will formulate the theorem, and this theorem says that we have some spectral sequence. We have initial page, and this spectral sequence converge to something concrete. Okay. Okay. To say it converges to something concrete, it needs to say what's the gradient and what's the filtration. And then convergence means that there are some such isomorphisms. there are general construction for spectral sequences, but we consider one not the most general, but general enough. It's enough general. It's spectral sequence of filtered chain complex. Now let we have chain complex. And that we have increasing filtration of this chain complex. It's increasing filtration of subcomplexes. Okay, it's all subcomplexes of this chain complex. We will assume after the very beginning that this filtration is locally finite. It will be enough for our assumption, for our applications. So for each fixed degree, this filtration is finite and good. So for some degree, for any such, no, just one second. No, yes, for any degree, for very big numbers, this is just Cn itself, and for all enough numbers, it's 0. These numbers can depend on n. Okay. 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 It's finite filtration such that the biggest part is Cn itself, and the smallest part is 0. But the length of this filtration may depend on n.
By the way, when you say filtration of chain complexes, you mean the filtration of each module?
It's filtration by subcomplexes. It's filtration each module, and it's preserved by differentials. With subcomplexes.
Preserved how? Is there any property?
What is subcomplex?
Quotients? No, I understand what is subcomplex.
No, this is just subcomplexes. In this, I have inclusions of subcomplexes. In each degree, it's submodule, and differential is the restriction of differential on this submodule. It's just subcomplex is just a submodule in each degree, which is preserved by differential.
Yes, okay, but because some people, when they say about filtered modules, they think about, say something about additional structure of the quotient.
No,
this is not our case, okay.
No, it's just number of inclusions of submodules, with increasing numbers. And it's locally finite. These boundaries may depend on n. Okay. Now then theorem. There exists spectral sequence of homological type. Homological type is what for indexing conventions. There exists spectral sequence with the first it begins from 0 page or from first page. No, I will indicate the first page. With the first page, it's homologies of the quotient complex as you wished. And it converges to homology of the whole complex. So, no, yes, and here I need to say what the filtration on the homology of chain complex. So, because to say that it's converged, I need some filtration here. No, filtration here with filtration FPHNC is just, no, it's just image of the filtration. It's just image in end homology of inclusion of filtration. By long sequence in homology is the same as kernel of projection on quotient, if you wish. It's some increasing filtration homologies, and I claim that quotients of this filtration homologies are isomorphic to infinity page of this spectral sequence. So
only for r equal to 1.
What?
You have E only for the case when R.
No, I say from what we begin, yes.
Okay.
No, from construction we obtain all pH. This is beginning. So what's idea? That if we have filtration, if we have some chain complex, we want to calculate its homologies. Maybe it's complete, but yes, but complete. I want to say complex. If we, sorry, maybe they are complicated. Maybe they are complicated, and but we can consider some filtration, and in general we can consider such filtration such that quotients much easier than original complex, and their homologies much easier. This is very easy maybe. The initial part. Of course, we have some spectral sequences, maybe not obvious, but in some cases, we will say something. And in infinity page, we obtain something, associated quotients of the homologies of C itself. Its idea begins from something very easy, and in infinity page, obtain, say something about what we want to say about the homology of C itself. Okay. Okay. Now let's construct this spectral sequence. Now let's start from 0 page. No, 0 page. No, we see that it's homology of something. So this is 0 page. Must be this spectral sequence. So okay, let's 0 page is this thing. Quotient modular. Yes. Because of this is subcomplexes, this quotient is also chain complex. We have vertical differential as we need, 0 differential, Q minus 1. It goes to same filtration, but decreasing gradient and chain complex. Okay? It's our 0 differential. It has to be degree 0 minus 1. Okay. Okay. Let's denote, we have this short sequence. I have this filtration. It includes, minus 1. It includes to the pth filtration. And this is quotient on this E0 module, on the quotient. It's projection on the quotient. Okay. Consider the following submodules. Oh, maybe. No, but if we consider this quotient module, what is kernels of this differential? What's 0? What's the kernel of this differential? It's such elements which goes to the previous filtration. Our filtration is such that for very small numbers of filtration, it's 0. We want to obtain what cycles? It's kernel which goes to 0 truly. But here I obtain only such elements which goes to one filtration below. I can generalize this observation. I can consider such submodule. It's R approximation for cycles. It's just elements from Cp plus Q, which goes from P filtration of Cp plus Q, which goes under differential of C to the P minus R filtration. It's R approximation for cycles. Okay, so I have filtration. In fact, it will be a lot of formulas on desk. Maybe it's better to write it down. Okay.
I have a recording.
Okay. Oh, it's very good. It's also recording. Yes. I have this one. What is Z0? Z0 is just it's all elements, no, its filtration is preserved by differential, so any elements of this filtration goes to P itself. So it's all filtration, okay? Because my filtration is preserved by differential. So if I start from Fp, it's differential also in Fp. It's always true, okay?
Okay.
Then I have, which goes to 1 below. If I go 2 below, no, my filtration is increasing, so it's also 1 below, okay? If my differential in Fp minus 2, P minus 2 contains in Fp minus 1, so I have this inclusion here. And so on. PQ. For my locally finiteness assumption, for big enough number, my filtration must be 0. So my filtration in fact stabilized, and I have stabilization infinity term, which is what? By locally finiteness, I have stabilization, because for big enough R, this filtration is just 0. So it's just kernel, okay? It's just intersection of kernel of my differential with my Fp filtration. Okay. No, and also I can consider there are approximations for boundaries. What is boundary? Boundary is something, no, which is boundary of something, okay. But maybe it's boundary, okay, let me see. It's maybe it's boundary of something which goes from some filtrations below. Okay, let me define. BR, PQ is by definition, it's index. Yes, it's D of Z R P plus R Q minus R plus 1. Yes. It's something which is boundary of some of some filtration of R elements above. Yes, no, it's no, yes, it's true. Yes. No, by definition of Z, these elements lies in Fp. Yes, because by definition of Z, if it's from ZR, it's degrees filtration on by R. Yes, so it's in fact lies in degree Fp of Cp plus Q. P plus Q. Also, you can check that this is gradient P plus Q plus 1, and so D in gradient P plus Q. So it's a module. So it's boundaries which boundaries of something of R filtration above. If R is infinity, it's just boundary because our F infinity filtration is all. But maybe it's boundary of some, no, it's of some smallest filtration of concrete smallest degradation, small concrete filtration, not very big, but maybe we know it. Okay, it's just definition. No, maybe I can say that. No, yes, it's okay. And so I have also filtration of these modules. I have B0. What is B0? No, it's D0. It's just no, it's just image of this filtration itself. Because by definition in this filtration, no, the smallest assumption is D of something from this filtration. It's D of Fp itself. And then it's maybe B1 PQ. It's something from filtration 1 above.
So what is this?
No, in fact, okay, maybe I can say this. This is, in fact, it's just Fp plus R, P plus Q plus 1 intersect with FP C plus Q. So this is just elements of this filtration, which is boundaries of this plus R filtration. This is by definition. So these elements, it's elements of this P filtration, which comes from, which is boundary of something of one filtration above. So my filtration increasing, so it's boundaries of something more. So it's more, it's a greater module. Okay? And so I have these inclusions, and again from locally finiteness, yes. For big enough R, my filtration in this fixed gradient is just hold this chain complex component, and so I obtain B infinity PQ. Is just image of D boundaries, which are also in our P filtration, because I want to be in my P filtration. In fact, it's easy to see because it's boundaries of something. So if I apply another boundary, I obtain 0. So in fact, of course, all this B are in all of this Z. So in fact, I have something like this: B0 PQ, B infinity PQ. Okay. Because image of something, of course, in kernel. Okay. Okay, let's return to this initial page. What's the kernel of this differential? Kernel of this differential. It's such elements which goes to the one below filtration. It's by definition Z1. It's Z1 PQ. Modular what I have if I consider in this module. Modular this filtration itself. Because all of this filtration goes to itself, but maybe there are some elements which is not in this filtration, but differential of them in this filtration. This is this quotient. It's the kernel differential, okay? Differentials of all of this goes to this because we have differential. But maybe there are some elements which is not in this module, but whose differentials are in this module. This is Z1. It's elements from FP on the one filtration above, but which goes to FP minus 1 after applying the differential. Okay. It's pi of Z1 PQ. Pi is projection. Projection modulo P minus 1. And what's the image? Image of the previous one, because I want to understand the homologies. Image of P. PQ. Okay, what's PQ? Or maybe PQ plus 1. The previous one. It's differential of P itself. It's B0. It's B0. Also modular. It's exactly P Q plus 1. Sorry. Sorry, PQ. Sorry. P plus 1 here. Because I want that this modulus contains in FP P plus Q, in gradient P plus Q. So it's boundaries of P plus Q plus 1, okay? Because I want to live in P plus Q gradient, okay? Yeah, then this is by definition PQ. Modular the same thing. This thing in fact not in this, so I need to consider its quotient. Its intersection. Okay. This is pi of B0 PQ. So consider homologies. I have homologies. From the one hand, homology of this chain complex is just homology of this chain complex. So the first page, if we construct spectral sequence, this is just homology of this chain complex, of this quotient. It's, as I said before, it's just quotient. Okay. On the other hand, it's isomorphic to this Z1 PQ modulo F minus 1 modulo B0 PQ modulo the same thing. Okay. Now let's consider what is this. With some general facts about quotients of modules. There will be 5 facts about this module, about these quotients. It's very easy exercises. No, it's really easy. It's maybe obvious, yes. At first, if I have yes, maybe it's better to rewrite this as I did it before. It's pi Z1 PQ modulo pi B0 PQ. Okay, if I have some quotient, some projection on the quotient, okay, and if I have 2 submodules, C, D, then what is the quotient PC modulo PD? It's isomorphic to what? No, in general, it's isomorphic to C plus B modulo D plus B in the first exercise. In the second exercise, it's isomorphic to, this is already isomorphic to C modulo D plus B intersects with C. No, I think it's more or less, if it must be more or less intuitively clear. Yes. Because pi is quotient modulo B, so pi of something is C modulo B, so it's clear. No, and here I consider C plus B modulo D plus B. It's the same thing as C modulo D, but maybe also modulo B, which also in C. No, it's easy. Okay, so if I apply this to my first homologies, I obtain that P1 pi of Z1 PQ pi of B0 PQ is isomorphic to Z1 PQ modulo, this is submodule. This is C, this is D. This is pi, A, B, and it's pi. Yes, this is B0 plus Z1 intersects with kernel of my quotient. Kernel of my quotient is P minus 1 filtration. P minus 1. It's my first homology. It's my first page. Okay. Now let's notice what is this intersection. In general, if I have the RPQ intersects with P minus 1, CP plus Q. What is it? Its elements from FP. No, in fact, from P minus 1. Yes. such that the differentials lies in Fp minus R. Yes? So it's elements from Fp minus 1, which differentials lies in Fp minus R. No, it's the same thing as Z R minus 1 P minus 1 Q plus 1. They, in fact, in this filtration, and they below filtration on R minus 1, in fact. So it's in this filtration in R minus 1. No, this is gradient P plus Q. So this is Z R minus 1, P minus 1, Q plus 1. So this is, in fact, Z1 PQ, B0 PQ, plus Z0 pi minus 1 Q plus 1. Okay. Now, no, we obtain 0 page, 0 differential. I have the first page. We need to construct the next differential. I want to construct differential on this page of the B degree minus 1, 0. No, it's easy, in fact, because now I have my differential of C. It sends Z1 PQ to, no, by definition it's B1 PQ. It lies in Z1 P minus 1 Q. Okay? It's by definition, it's obvious, because any B, just 1 second. No, sorry. Q, what, here, it's by definition, yes, it's by definition, and any B lies in any Z. It's obvious. Yes, this is by definition. No, and also D of Z0, P minus 1, Q plus 1. No, I want to apply D to this. D. The first part goes to this one, at least. The next, the quotient part, no, this goes to 0 because it's already boundaries. And this goes to B0 pi minus Q plus 1. It lies in Z0 pi minus Q plus 1. So at least it lies in 0 here, B0 pi minus, Z0 pi minus 2 Q plus 1. It's image of this. No, and I can quotes also by something else. I quotes by this one. And this is by definition E1 P minus 1 Q. This is E1 PQ, and this is my differential, D1 PQ. And I can do this in general. In general, I can define ER PQ as ZR PQ modulo BR PQ plus ZR minus 1 P minus 1 Q plus 1. So this is R cycles, modulo R boundaries, and modulo, this is just R cycles which are in the previous filtration. I don't want to consider this, I consider this previous filtration, in fact, in the previous steps. So I don't want to consider this in this step, so I quote by this. And by the same rule, I have the same differential. In fact, I have the same differential. The differential of C induces, this is to B and then to Z of P1 minus 1, minus R. Maybe I need to clarify this. No, because d of ZR PQ, it's by definition B R P minus R Q plus R minus 1 is by definition. So it goes to B, and B lies in Z, so it's particle of this case. And also this goes to B and then to Z. R minus 1, pi minus R minus 1, no, plus R. And something which we want to see here. And this is my R differential. Yes. No, we can define this. We need to check that this is spectral sequence. We need to check that it's differential and it's homologous, isomorphic to the same thing, but for R plus 1. It's what we need. No, this is also, as we said before, this is projection of ZR, PQ, and BR, PQ. So we just minus 1. So we consider R cycles and R minus 1 boundaries, but modular previous filtration just. No, it's not important, I think. It's true. Okay, we need to calculate kernel and image and calculate homologies and obtain that this is of the same form. Okay, let's check this. Yes, this is E R P minus 1 Q plus R minus 1. Kernel. What the kernel? Kernel of this map. Okay. No, again, easy one. Easy algebraic fact that if we have map from A to B, and I have submodule C which goes to submodule D, so I have induced map of quotients A to A modulo C to B modulo D. And what the kernel of this map? If you consider induced quotient map, what is kernel? No, it's elements which goes to D, yes, and F.
Of course.
So it's preimage of D, modulo what? No, modulo C, which lies in D. So modulo intersection with C. Okay?
It was a question for me.
Yes.
Okay.
No, of course. Yes. Okay. So no, this map induced by our differential. So yes, so kernel of our differential, it's preimage D minus 1 of this group. Maybe I need some, no, I will denote it by brackets. Modulo this preimage intersects with C. C is this group, or it's another bracket. It's 1, it's 2. It's 1, bracket 2. Okay, and now I want to understand what is this. The last easy fact from algebra. If I have two submodules, maybe I need, yes. If I have two submodules of C, then I can consider, no, if I have, then I have A modulo B, and I can consider C modulo B intersects with C. And I have no natural map induced by inclusion of C to A. This is inclusion. It's always injective. No, and the question, what's the image and or when it's surjective? When it's isomorphic? If and only if, what? It's a question for you.
B intersect with C?
Mm-hmm.
But B lies in C.
Sorry. No, I have A modulo B. I consider the induced map from C to A modulo B. Its kernel is exactly B intersects with C, so it's injection. And when it's surjection, what's the image? What's the image of this map? No, okay, when it's surjective. When it's surjective. Now I need that any element from A, modulo elements from B, comes from C. No. C coincides with A modulo B. What does it mean? It means that A equals B plus C. So A coincides with C modulo B. Okay? No, if it's not clear, you can think about this. Okay. In our situation, I have this quotient of this form. No, sorry. I have this is quotient of this form. I can consider. I want to consider some smaller quotient, which is in fact the same quotient. This is A. This is B. I want to consider another C in A. C in A. It's my preimage of my first bracket. And C is in fact Z R plus 1 PQ. No, the first one. This submodule. This is submodule of A. So image of this Z under D lies in this one. No, it's because D of Z R plus 1 PQ. It's by definition B R plus 1 P minus R minus Q plus R. And this is lies in Z R minus 1 with this lies in this lies in this. This lies in Z R minus 1 minus R minus 1 Q plus R. What? But because it's differentials and their differentials goes to 0. So in fact, of course, it belongs it to R minus 1. We need only these gradings. We need only these gradings. Well, this is true. Okay. Okay. So image of this C lies in this bracket. Namely, it lies in this part. Okay, so it's submodule. No, and we need to check this. No, I want that this submodule. I want to check. No, I want to goes from this quotient to this smallest quotient. Oh, maybe no. Yes, maybe what is the B intersects with C? B is this big one. When we intersect with C, what is this? No, in fact, it's easy thing, because yes, what? No, okay. I already seen that C lies in A. This is intersection. This is A intersects with something other. So this is C intersects with A intersects with this. Yes, okay. No, with this second bracket. But this is also C because C lies in A. So it's just intersection C. So it's just Z R plus 1 intersect with this bracket. B R P Q plus Z R minus 1 P minus 1 Q plus 1. What is this? Sorry, stop. Oh, sorry. R minus 1 was here. It's minus 1. It's by definition. Yes, sorry. It's by definition R minus 1 here. Sorry. No, because it's 1 and 0, 0 here. Sorry. It was typo. -1, yes. Yes, then, no, this B lies in Z, it's always true. So this intersection is B, it's the same B. So this intersection is B, because any B lies in any Z with the same gradings. And what this intersection? These intersections, no, again, it's elements from P-1 filtration, which, no, it's elements, what this intersection? By definition, what is it? It's elements from P filtration and P-1 filtration. P-1 is smaller, so it's elements from P-1 filtration. It's elements from P-1 filtration, C, P plus Q gradient. And its image goes to P minus R minus 1, P minus R. P minus R is smaller. So it goes to Fp minus R. Okay? No, and what does it mean? This is just Z P minus 1, Q plus 1, R plus 1. Ah, sorry. This must be R. Ah, no, just R. Just P minus 1. Ah, sorry. This is smaller. Yes. P minus R minus 1. It goes to deeply. Yes, it's minus R. Yes, it's R. Mm-hmm. Okay. Well, this intersection. So this intersection is exactly the B R minus 1 PQ plus Z R pi minus 1 Q plus 1. Well, so it's so no, it's not no. In fact, no. Yes, it's not very scary quotient. This quotient C modulo B intersects with C is just what is this? C. What's B intersect with C is just no my C R plus 1 PQ no modulo B R minus 1 PQ plus Z R P minus 1 Q plus 1. It injects to my kernel, and I want that this is surjection, so I want to check this property. I want to check that this is isomorphism if and only if A is my preimage of the third bracket. A D minus 1 of first. It's sum of B. B is this big one. Okay, it's B. No, plus my C plus 1 PQ. No, in fact, this is very easy. Equality. No, okay. No, maybe yes. Maybe what is A? B is A. This is A. This thing is A. Intersects with second bracket. No, second bracket I already bracket. I already write down here. This is the second bracket. With B R minus 1 PQ plus Z R minus 1 minus 1. Mm-hmm. Okay. So if I consider this thing and this thing, is it true? No. Yes. No. Okay. Let's consider some elements from here. What does this mean? This means this means that what X A from A. No, this means that dA is from the first bracket. The first bracket is this one. This means that dA lies in B. Yes, B R minus 1 P minus R Q plus R minus 1 plus Z R minus 1 P minus R minus 1 Q plus R. Mm-hmm. No, okay. dA is some d, I don't know, b plus z. This is from this is from this. In fact, no, this means that in fact b is from, no, by definition of b is d of z, of something, yes? So in fact b is from z, no, with the same numbers. R minus 1, p minus 1, q plus 1, in fact. No, okay, I obtain what? And yes, and this is from here. No, okay. So I have this A and B from where? Yes, and A, yes, and sorry, and A is from no, yes, okay. What does it mean? This means that D of A minus B is Z. Okay, and Z lies in this part, but it's only important that it lies in P minus R minus 1 filtration of something. No, this means, but and where lies A and B? No, in general, A lies in no. In general, A lies in P filtration. A lies in P filtration. B lies in maybe something smaller filtration, but in general, this element lies in P filtration. And its image lies in P minus R minus 1 filtration. So this means that this element lies in Z P, no, там, вот Q, or yes, Q, R plus 1. Yes. And this is my element from C. So I express my element A as B plus element Z. No, not Z, no, it's plus A minus B. It's from Z R plus 1, PQ. And this element B, no, it's from, yes, sorry, on B from, I read it before. Yes, it's from this. Yes, sorry. It's from Z R minus 1, P minus 1, Q plus 1. It's by definition B. And no, and it's here. It's from this. This is from this, and this is from this. This is not quotient. Yes, this is one summand and another summand. This is one summand and this is another summand. So it is from two summands, and so any element of A is sum of this and this. So this is isomorphism. So this is my kernel. Okay. No, image is easier than kernel. In fact, it's almost all. Sorry. For the image of my map, of this map. No, image is by definition just. I think we don't need any algebraic facts for. Yeah, no, sorry, no, maybe. If I have this induced map, what's the image of this induced map? Image of this induced map, it's image of F. No, modular image of F intersects with D, yes? No, it's obvious. No, okay. But this, the image of this map is by definition B. So image of this thing. No, okay, let's consider image of the previous R, minus R plus 1. Its numerator is by definition some B of something, B R P Q in fact. And modular its intersection of this image with this quotient, So it's B R P Q modular intersects with this thing. R minus 1, R minus 1, R minus 1 Q plus 1. No, it lies in, no, sorry. Oh, yes, I cleared this, but BR lies in BR minus 1. It's increasing filtration. So this intersection is BR minus 1. And here, no, you can check that this intersection is just B R P minus 1 Q plus 1. It lies in this. It lies in this. So in general, you obtain finally, as a result, you obtain that this is isomorphic to BR PQ modulo BR P minus 1 Q plus 1. Finally, all these things lies in this. Okay, yes, you can check this. Okay, it's my image. It's easier than the kernel. And so what the homology is? It's kernel, image. Or what the quotient? Homologies PQ of my rth page under my rth differential. Its kernel Z R plus 1 PQ modulo B R plus 1 P R minus 1 PQ plus ZR P plus 1 Q minus 1 modulo B R PQ modulo B R P minus 1 Q plus 1. Yes. Now this thing contains this thing. So this is isomorphic to, no, it's this thing modulo all of this, yes? No, this thing is greater than this thing. So this is this modulo this, the biggest one, and this thing, okay? That's what I want to say. ZR plus 1 PQ modulo this thing, it's bigger than this one, and this thing maybe. Also need this. Sorry, it's here. It's a typo. It's minus 1, Q plus 1. Yes, minus 1, Q plus 1. It's here. It's here. It's correct. Minus 1, Q plus 1. No, and this is by definition my ER plus 1 PQ. In fact, it's correct. All coincide. So we obtain spectral sequence. We define big rate modules, differentials, and the homology of differential in the next page. And we already have the next differential and so on. So it's spectral sequence. Why it converges to homology of the original complex with the induced filtration homologies. Now what the infinity page? Now we have the formula for R page. What the infinity page? Now we have Z infinity, B infinity, Z infinity. Infinity page. No, maybe it's easy to say that, as I said before, in fact it's pi ZR PQ modulo pi BR PQ, as I said before, where pi is projection on the quotient, infiltration of the original complex. So infinity, it's pi Z infinity PQ pi B infinity PQ. Maybe not R minus 1, but it's also infinity. Okay. Now what is the infinity? The infinity, it's kernels. It's kernel of my differential, which in P filtration. And V infinity, it's image of my kernel, which in my filtration. Yes. Okay. No, yes, maybe. Yes, maybe. No, maybe it will be better of the previous form. Sorry. No, it's the same thing. Okay, like okay. BR minus 1 PQ plus ZR minus 1 P minus 1 Q plus 1. And so infinity is Z infinity. It's B infinity PQ plus Z infinity P minus 1 Q plus 1. But we have already seen that this thing is in fact intersection of Z infinity with the previous filtration. Yes, the previous filtration. What does it mean? We have seen this before for finite R. What? So we have that it's kernel of my differential intersect with P filtration modulo image of my differential modulo P filtration plus kernel of my differential in the previous filtration. No, it's more or less obvious that this is isomorphic to quotient in homology. So I recall that in homology I have induced filtration. So Fp of my P plus Q homology is image HPQ of P filtration. And I want to consider quotient by Fp minus 1. No, so it represents by some kernel of my P filtration, modulo kernel of previous filtration, and modulo images because it's homologies. No, more or less, you can check that this is isomorphic. No, it represents its element of homologies. It's some cycle, which in fact image of cycle in filtration. So it's cycle in filtration. Modulo, no, image is filtration because it's homology, and modulo cycles of the previous filtration, modulo all cycles in previous filtration, all homologies of previous filtration. Okay, it's more or less clear, I suppose. I believe. Okay, clear or not? No, it's more or less clear that this is the same parts. It's some kernels in P filtration. It's kernels in P filtration. It's kernels which comes from P filtration, the image of homologies of P filtrations. It's images in P filtration because it's homologies. It's modular images of P filtrations. And kernel in the previous filtration is all homologies of the previous filtration. We consider quotient by them. Now you can check that this is isomorphic. Okay. Let's leave it as an exercise. It's the final part. Now it's relatively easy. Direct check. So, okay, we have that the infinite page is the quotient of these homologies. Okay. No, check this. If it's not obvious, okay. It's all. It's a construction of spectral sequence of filter chain complex. Example. Let's consider example. Spectral sequences are useful by examples because it's tool. Meanwhile, there exists a relatively deep theory of spectral sequences itself, but we will use it as a tool. Example. Consider chain complex with the most short filtration as it possible. No, the shortest filtration is some chain complex itself, length 0. Consider filtration of length 1. It's some chain complex with some non-trivial subcomplex, and it's all. It's all my filtration. Okay? Now denote it, for example, I don't know, it's F0, and this is because I want that my filtration must be increasing, this is F minus 1 then. Okay? Then it's 0. and consider the corresponding spectral sequence. I have, yes, zero page. 0 page. It's no, it's by definition, it's quotient fp c plus q modulo f p minus 1 c plus q. What is it? No, my p is only 0 or minus 1, yes? If p is 0, then it's p is 0. Okay, let's p is 0. This is then c q modulo u q, yes? It's quotient module, a quotient chain complex, okay? If pi is minus 1, what is it? U q minus 1. It's 0, but it's, yes, it's u minus 1. So on the 0 page, I have on the 0 column, when p is 0, it's c modulo u q, c modulo u q minus 1. No, with induced differential, because if I have chain complex on quotient complex, I also have differential, yes? This is quotient differential. And also on the p minus 1, I have u itself, but with the shift. This is q minus 1, q minus 2, no, with the differential itself, okay? It's my 0 page with 0 differentials, vertical one. If I consider, no, then let's start compute other pages by computing homologies. Homologies. The first page then is a homology of this thing. No, okay. No, we also have these two columns, and we obtain the homologies. P0, P minus 1. It's homologies. C modulo U. Homologies. C modulo U. And this is homologies minus 1 of U. Homologies Q minus 2 of U. And so on. And also we have horizontal differentials. By definition, we obtain the horizontal differentials. So we obtain some differential Q from HQ C modulo U to HQ minus 1 U. No, okay. Let's compute the next page. Next page is the homology of these short chain complexes. The homology is kernel and co-kernel of these differentials, as we know. So the second page, it also has two columns, P0, P minus 1. In this column, it will be kernels of the differential, and then it's co-kernels, yes? Kernel of D1Q, and this is co-kernel D1Q, and so on. And here all differentials are 0. All higher differentials are 0 because we have zeros here. All other differentials, they also have 0 or 0 target or 0 source, okay? So in fact, this is infinity page. We have all, no, this is situation when we have one global n, where all PQs. It's because we have a lot of zeros. Okay. So, on my homologies, no, okay, I have some filtration on my homologies. Yes, what my homologies, P plus Q of my C. I have some filtration, but I know that graded quotients of these filtrations, not 0, my infinity pages, only if P is 0 or -1. This means that in fact, and I know that my filtration is finite and it's good. Its union is all homology and its intersection is 0. This means that in fact the first, this is the 0 filtration, in fact. Then I have -1 filtration. And then is zeros. And this quotient is infinity P. Что там говорил? Это минус это. Получается infinity -1 P plus Q -1. Yes? And this quotient is infinity 0. P plus Q. No, if you have some another filtration, you have all other quotients are 0, so from this it's stabilization. But we know that it's stabilized on 0, so it's a 0 itself. And here also, we have all other quotients are 0, so this is stabilization, but we know that the union of all of them is all my homology, so they stabilize on the whole homology, okay? Because of 0's quotient, the filtration stabilizes. And we know that it's stabilized to 0 and to whole homology, so this is equalities here, okay? It's the most important moment. We use it all together. It's if we know that in our spectral sequence we have only 2 columns, then in fact we have only 2 filtrations on the target thing. Okay? No, maybe you have some filtrations. What? Maybe F0, F1, then F0. So, but this quotient is infinity 1. This is 0. So in fact this is equality here. And so on. It's equality to F0. All other are equalities. But I know that the union of my filtration is whole homologies. So it's stabilized in the whole homology. And so here it also stabilizes because all quotients are 0. But I know that intersection is 0. So they stabilize at 0. On this step again already. This is not 0, but all other quotients, will be already 0. Okay. So, in fact, I have only 2 non-trivial filtration parts. Okay, and so I have 2 extensions. Oh no, sorry, I have 1 extension. Oh, yes, because this is quotient with 0, so in fact it's equality, and this is extension. So I have extension of the sort E infinity -1 P plus Q plus 1. It's the -1 filtration. It includes to the whole homology. And quotient is this E infinity page 0 P plus Q. And here 0, it's kernel of D1Q. It's kernel of D1Q from, so we don't need this. D1Q is kernel from H. No, sorry, it's not Q, it's P plus Q, yes. P plus Q. P plus Q to P plus Q minus 1 U. And this thing is co-kernel of G1 P plus Q plus 1. No, the same thing. H P plus Q plus 1 Q to U. No, and in fact, if you have such short axis sequences, then you can glue them together to one long axis sequence. In fact, it's equivalent to say. It's equivalent data as one short long axis sequence. So we have what? We have H P plus Q C. It subjects onto the kernel of map. Kernel of map from H P plus Q C U to p plus q minus 1 c modulo u. Now, if we suggest on the kernel, it's the same thing as, it's the same thing that, yeah, sorry. One second. The kernel of this map yes, and suggestion on the kernel it means that this map this sequence is exact in this place. Okay. Правильно? Yes. No, and in fact you can check that this map induced by the quotient. And on the other hand, you have inclusion of this thing, and this is co-kernel. In fact, you have h p plus q plus 1 c u. It goes to h. Just one second. H p plus q plus u, and it has co-kernel. And we have inclusion of this co-kernel. This means that this sequence also exact in this place. And in fact, you can check that this. No, so in fact, you obtain exact sequence of some form, may be familiar. In fact, it's long-range sequence of homologies of this short-range sequence of complexes u, c, c modulo u. No, so what the result? So we obtain that the simplest example of this spectral sequence gives you the long-range sequence of homologies. It's the simplest example. If you have the shortest filtration, you obtain something which is equivalent, gluing data is equivalent to one long-range sequence. It's a bunch of short-range sequences, but in fact they are equivalent to say that we have one long-range sequence, and you can check that this is exactly the long-range sequence of this short-range sequence. This is this map induced by inclusion, this map induced by quotient. No, and we have some differentials here. This is differentials, and this is boundary maps, in fact. So this is the first example. For the shortest filtration, which is possible, it gives us long-range sequence. For longest filtration, it's kind of very far generalization of this long sequence. They kind of they're kind of gluing from this a lot of long-range sequences of all of these short-range sequences in one filtration, something like this. No, so the point that for not very short filtration, we obtain that it's not just long-range sequence, it's a spectral sequence. Now, for example, even if we have filtration, it's finite only in one on each n. It's not be finite in general. So in fact, it's not finite filtration, and so we obtain some infinite pages spectral sequences. No, it's very vast, very far generalization of this long-range sequence of homologies. Okay. No, it's clear that it works.
This is clear.
Okay. This is clear that that's the example of spectral sequence is the long-range sequence. Okay. Okay. Let's consider then the particular case of filtration, which we will use for Tor and Dex and so on. It's some Tor example. Let's consider a real example. It's situation of Bicomplex. What is Bicomplex? No, it's just complex of complexes, kind of this. Yes, it's B-graded modules, and we have vertical and horizontal differentials. I have, I don't know, first differential. No, vertical one, yes? And horizontal one. Maybe. If it will be important grading, maybe vertical and horizontal. And no, and I want that, for example, this squares compute. Okay, this squares compute. Something like this. No, maybe they're not compute. I want they're not compute, they're anti-compute. Okay, I want something like this. No, it's not important. If they compute, you can change some signs to obtain that all squares anti-compute. And if they anti-compute, you can change all signs except of all even signs. If you change all even signs, you obtain that will be zeros here, minus here. And if you change even signs again, you obtain plus. Okay. So in fact, if you have this thing, it's equivalent to say that for very easy rewritten of one of differentials, no, for example, change of some signs, you obtain minus here. It's not important. So it's equivalent to say, but no, it's a little bit better because no, this means that okay, this is Bicomplex. It's definition. Okay, definition of Bicomplex. I want this convention for compatibility of these two differentials. And then for Bicomplex, I can consider its total complex. Yes, total complex of Bicomplex. It's chain complex. It's and think it's direct sum of C P Q. P plus Q is N. It's sum of diagonals on one diagonal. Sums of diagonals and no, and differential. It's sum of two differentials. Differential. It's sum of two differentials. No, because these two differentials from this diagonal it goes exactly to
Another diagonal, I guess.
What? Yes. So 1 second. Something wrong here. No, yes, of course, because my horizontal differentials it's must no PQ. Yes, sorry. P minus 1Q. Yes. Okay. No, they decrease my gradings. All both my differentials decrease my gradings. I just inverse one coordinate. Okay, horizontal coordinate. Yes. Sorry. So yes, my and now because they decrease my gradings, they decrease sum of gradings, the number of diagonal. Okay. And I can consider its formal sum in direct sum. And it's differential because it's square of sum, and square of sum is square of the first one is 0 because it's complex. Yes, I don't say. Of course, they compute, and all rows and all columns are chain complexes. Yes. Of course. So it's Bicomplex. And this is equivalent. It's equivalent to say that the sum is also 0. But to say this, we need to formulate what is sum because in different directions. But if we consider formal direct sum, this is equivalent to say that this because it's just sums. And this is in fact in different direct sum. So this 0, if and only if this is 0. So in fact, so I obtain some differential on my total complex. So it's a chain complex. Let's say called total complex. Okay, and so and on this chain complex, on total complex or some Bicomplex, I have two. No, they sometimes called stupid filtrations. No, I don't want to say this. So some standard filtrations, two standard filtrations. Horizontal and vertical. What the first filtration of my total complex is just or something like this. It's in gradient n, then it's sum of C PQ, P, ой, P, it's плохо. Oh, sorry, IJ. I plus J. It's n, and I less than P. It's element in my total complex which have the first coordinate not greater than P. In my chain complex, it's something like this filtration, or this, then this. It's increasing filtration, and oh yes, it's increasing filtration. Okay. Yes. If, for example, oh yes, it's increasing filtration. And I have another filtration, vertical one. It's bounded by P above. It's also increasing filtration. My chain complex, they are not locally finite in general, yes, because if I have in some fixed n, I have maybe infinite diagonal, and then I have infinite filtration, okay, in general. If I have some infinite diagonal, then I have infinite filtration. But if all my diagonals finite, then this filtration also finite, locally finite. No, for example, if if in Bicomplex all diagonals finite, then these filtrations locally finite. For example, if my Bicomplex in the first quadrant, then all diagonals finite, and so the filtration is locally finite. And so we have spectral sequences converge to homologies of this total complex. And we have two spectral sequences. And yes, and this is important way of using spectral sequence. If we consider this spectral sequence, we obtain two spectral sequences. They're different, but they converge to the same thing, to homology of the total complex. And in some cases, it's very useful because we have something and something different. So we can analyze these two differences maybe by different methods. And the information that they converge to the same thing, maybe they are something. We will see it, I think, the next time. Now, I think, let's say what the initial pages of the spectral sequences. For example, the first one, yes? The first filtration gives us the first spectral sequence. What the 0 one? 0 page is quotients, yes? It's quotients of the P, total complex modular P minus 1. What is it?
This is CP.
Yes, in gradient P plus Q, yes, I have two numbers, which is sum is P plus Q. Yes, and the first number is not greater than P, and I consider its modular if they are less than P. So the first number is P and the second number is Q, so it's just CP plus Q, CPQ. It's isomorphic CPQ. So I have vertical differential, and this is my, it's, I have differential which, I have the first differential which increase the first coordinate. This is so-called our horizontal differentials, yes. This is our just horizontal differentials. It's just one of the differentials of my Bicomplex. It's the zero differentials of my spectral sequence. So if I compute homologies, I obtain homologies of my horizontal differential. So first page of my first spectral sequence is homologies of yes. Just one second. FP. The zero differential is vertical, the first and the. So the zero differentials is coincide the second coordinate. So it's in fact our vertical. Yes, it's vertical differential. And so we obtain that this thing is P is fixed, and we compute the vertical homology of this thing in Q place. And now we have horizontal one. Horizontal one. Now because of this equality, horizontal differentials it's correctly induced map on homologies under the horizontal one induced maps on homology with respect to the vertical one. No, because of this equality, it's correct. And this is exactly this thing. The first differential is just this differential induced by horizontal one in homologies. No, you can check this. By definition, it's clear. It's direct checking. So the second page of the first filtration of the first spectral sequence. The second page of the first spectral sequence is just homologies. It's just P homologies of Q homologies of our Bicomplex under the vertical one and then by horizontal one. And it converges to, if our Bicomplex have finite diagonals, it's locally fine, stabilizes, and it converges to homologies of total complex. And for the other spectral sequence, for the other filtration, you can do the same thing, but then the first one will be the horizontal one, and the second, the zero differential will be horizontal one, and the first differential will be the vertical one. And so you obtain, in fact, if you do this, you obtain that this is HP, HQ, in the opposite direction, just HDV. And it converges to the same thing. So, yes, if finite diagonals, then it converges to this thing. So we have two different spectral. No, in fact, if your Bicomplex is not symmetric, if it has different rows and columns of different nature, then in fact it's different homologies. You compute the first one and then another, and in different order. They usually not the same, but they converge to the same thing. So it gives us some information. We will use this on the next lecture. Okay, so.